Well, welcome back to physics, AP Physics. This is the second semester of our course. Just need to remind a few of you of things we've learned in the previous semester or last year, depending on when you had it. The first is called kinematics, and that's just a description of motion. So when you describe how things move, not necessarily why they move, it's called kinematics. The variables in kinematics are your location or your change in location, usually x. Some books use s and delta s. You could have your velocity at the beginning of the time you're looking, the velocity at the final moment that you're looking. You could have change in velocity. If you know the change in velocity and how much time it took, that's called the acceleration. And so those are the types of things that you look at in kinematics. There's a couple of ways to look at things, the motion of things. One is on a graph. And so if you had a graph of the position of something as time went by, and it went like this, let's say. Well, you can say, well, it definitely changed its location, because at time equals 0 it was there, and time equals something it was there, and it also looks like it moved in the positive direction until about there, and then it moved in the negative direction, and then it looked like it kind of stopped moving. So there's ways to describe that. One of the ways we studied was to draw a velocity time graph from the same situation. And we would say at the beginning, at time equals 0, it had a positive slope. And since the velocity of something is defined as how far it went divided by how much time it took, that is a slope. And so that'd be a positive slope of some steep value. So I'll put a dot there. About here, it looks like the velocity is 0 because it has 0 slope. And then here, it has a negative slope that's kind of steep. So I would say right there, it has some negative value. And then by the time it gets here, it has some velocity that's 0. So I'm not sure what the shape of that looks like in the middle, but we studied things like that and tried to decide what the velocity or the speedometer reading would look like as time went by. If you wanted to continue that, you could say, well, the acceleration as time went by, it looks like right here the velocity is changing in the negative direction. So that'd be a negative acceleration. Here, the velocity has stopped changing. So right there, you'd have a 0 acceleration. Here the velocity is moving in the forward direction from here to here, so there'd be some positive values in here, and then the acceleration looks like it's 0 there because the velocity is not changing. So there'd be some strange looking thing that kind of went like that, and those are hard to sketch, and we didn't do very many of those. But if you understand that the slope has meaning, then you can decide what these graphs would look like. One last thing, not necessarily it's kinematics, but in this situation here, since Newton's second law is F equals ma, as long as the force is constant, or it's not constant in this case, but if we look at it in that situation, and this tells you A, then the force versus time graph would be a same size, although shifted in magnitude because of the mass, but it would have the same general shape. That's kinematics. Now, there are some special cases where the net force is constant, in which case the acceleration is constant. So if the acceleration is constant, there's some things that happen. If acceleration is constant, the position time graph makes a parabola. Pretend that's a parabola. And the velocity reading, which would be the slope, steadily increases. This is for a constant force only. Okay. In this case, the velocity time graph looks like it's pretty much 0 at the beginning and getting more and more positive. If you have a velocity time graph with a constant force, you get a straight line. And if you look at that same situation, the acceleration versus time graph, well, there'd be a constant value of acceleration, so there'd be a horizontal line. These graphs, where you have constant acceleration, created some formulas. If we had a velocity that started off non-zero, we could write an equation of that line that looked like this. Let's see, the final velocity, some point in time out there, would be the slope, which is the acceleration, times the time plus the beginning velocity. And that formula there is one of the kinematic formulas for constant force and therefore constant acceleration. And there was a few of those. And that's just a quick reminder of kinematics. The next thing that I mentioned it just a second ago that we did was look at Newton's second law. Now Newton's first law is the law of inertia, which we'll come back to in class. Newton's second law says, well, if you know the force on something and the mass on something, you can figure out the acceleration. or if you know the mass and the acceleration, you can determine how big the force was. Now this force is actually the net force. So the most simple example of that would be something like this. If you had a car, let's say it was moving to the right, and it was a 5 kilogram car, and it had a velocity already, let's say going that way of 20 meters per second. If somebody came from behind and pushed with a steady force of 10 newtons, then I could determine some things. I could say, well, I know the force. Now this is for a steady force, and so I can say 10 newtons divided by 5 kilograms comes out 2 newtons per kilogram. A newton, if you recall, is a kilogram meter per second squared. So you get some canceling and you get 2 meters per second squared. That's the acceleration, just using this simple formula. That means if I know the acceleration and it's a steady acceleration, the velocity time graph would look like this. Let's see, it's going, I'll call that way positive. It's already going 20, and it's going to increase 2 meters per second each second. And so I could figure out, using a simple equation, how fast it would be going at some time in the future. That's the most basic rule. Now, when I said net force, if there was someone pushing this way with 10, at the same time someone was pushing this way with 8 newtons, well, there's a pushing match, and the winner is to the right, and it would only be 2 newtons, which would change all of this math. But the logic is find the net force, which is a comparison of all the forces, and then that is the net force, and then you can use the mass and F equals ma to find the acceleration. The third sort of thing that we did in this quick review is Newton's second law when the force is just for a length of time. When the force is on for a length of time, it's called an impulse. In fact, this is how Newton really did his rule. He said, that if you have, I'll do it backwards, F equals ma, but a is the change in velocity over change in time. If I multiply both sides by the time, I get force times the time equals mass times the change in velocity. Okay, or I could put the change in velocity out front, or the change symbol, and get that. This right here is how you figure out changes when the force only lasts for a length of time. In fact, Newton called this side an impulse, and he called the quantity mv together, he called it momentum. So here's the most simple situation. You could have a car, let's say it's 5 kilograms, and it's already going forward, I don't know, 10 meters per second. Someone could come and push it forward, increasing the speed. And if they pushed it forward with, 20 newtons, but they only did it for 3 seconds, could you figure out the final velocity? Well, yes, because in this form of Newton's second law, you could say the impulse was 20 newtons times 3 seconds, or 60 newtons times seconds. Now, there's no nickname for that. And that would equal the change in momentum. Okay, now momentum, in fact, this would be a positive change in momentum, and Newton used to speak in terms of, it gained 60 momenta. So what would that look? Well, anytime you have a change symbol, it would be the final minus the initial. Okay, so I could say 60 newton seconds equals m. Well, the mass doesn't change, so I'll factor it out. V final, I don't know, minus V initial, which was 10 meters per second in this case, and I could do some simple math. If I put the mass in there, I could determine the final velocity. Okay, now this is this reduces to the same formula we did just a second ago, but there's lots of times where an impulse is a much better way to look at what's happening, especially when there's more than one particle.